Let's do some quantum mechanics here. One-dimensional, time-dependent quantum mechanics, infinite square well. I've already made this program. This is a superposition of two energy states. Oops, I've clicked on the wrong thing. In an infinite square well. And so we see this oscillation that goes back and forth. But this is just saying, okay, I know these two solutions. I know sine. I know sine's a solution. I'm just going to plot them. So it's really just plotting a superposition of states. It's still cool. But what if I just started with that wave function? Could I let it evolve by solving Schrödinger's equation numerically? Yes. And that's what we're going to do. Okay. So let's jump over to the paper and let me talk about how to solve the time-dependent Schrödinger equation with the finite difference method. Jumping over to paper. Now I've had some focus problems with my camera, so if it loses focus, I apologize. So this is my one-dimensional infinite square well. This is my Schrödinger equation. I h bar partial of psi with respect to t is negative h bar squared over 2m second partial of psi with respect to x plus some potential. And even if the potential is 0 in here, I'm going to do this more generically for later purposes. So the problem here is that we have a complex number, right? If we separate this into a space and time component, we can get rid of that complex number and solve a real differential equation. But right now we have a imaginary number, but there's no imaginary numbers over here. So we can solve this by making two equations. I can make two differential equations by letting psi of x and t be some real component plus an imaginary component. So I'm going to assume it's a complex solution. It has a real part. Am my focus losing? Please don't lose focus. Okay, I think if I write down here, when I write up here, it gets out of focus. But when I write down here, it's not so bad. I don't know what happened, but something happened to my setup. Okay, and I don't know how to turn off autofocus. I'm using a phone. Yeah. So let's just plug this into this equation up here, right? So if I plug in r plus I to this, and I take the partial derivative with respect to t, I'm going to have the partial of r with respect to t plus I times the partial of I with respect to t. But I have an I times an I, so this is going to end up being an imaginary, and that's not. So let's just plug that in. Let's do the r first. I'm going to get I h bar partial of r with respect to t, right? I'm just taking the derivative of a sum is pretty easy. Now for this other term, I have the I times the I, so it's going to be -1, negative h bar partial of I with respect to t. Now let's do the other side. I'm going to do the same thing again. Now I'm going to take the partial derivative, the second partial with respect to x of a sum. So I get negative h bar squared over 2m, the second partial of r with respect to x. And then this second term has that imaginary number in it, minus I h bar squared over 2m, second partial of I with respect to x. And then I have two of these terms, v times r plus vr, and then I have plus ivi. But what we've done here is to make two equations, right? Because over here I have a real and a complex part. Over here I have a real and a complex part. In order for this to be an equation, the real stuff has to be equal to the real stuff. The imaginary stuff has to be equal to the imaginary stuff. So let's start with the imaginary stuff. If I have an imaginary function here, I h bar partial of r with respect to t, and negative I h bar squared over 2m, this. Well, I can leave the i's off. They're going to cancel. So I can write this as the real equation, h bar partial of r with respect to t equals this, negative h bar squared over 2m, second partial of I with respect to x squared, and then this term right here, plus vi. So that's a differential equation that I can deal with. Now let's do the same thing for the real stuff. So right here I have a real negative h bar partial of I with respect to t equals the real stuff right here, negative h bar squared over 2m partial of r with respect, that's messed up, respect to x plus vr. So I have two similar looking equations, but notice that I have these two functions r and I. And so this has the time derivative of r is related to the space derivative of I, and this has this time derivative of I is related to the space derivative of r. And the only difference between them is this one is positive and that one's negative. So that's good. Okay. Now, how do we make this happen with the finite difference method? I'm going to scooch this up because I feel like I do better if I write on the lower part of the paper in terms of focus. Suppose I look at just the r function and I break it into finite pieces right there. So I have R0, R1, R2, R3, R4. I have finite elements, and they're spaced out delta x, delta x, delta x. Now, in that case, I can write this second derivative of r with respect to space as a finite difference. So what I'm going to do is I could write the partial of r. I'm going to call this ri. This is the ith element, right? Ri with respect to x could be written as a half interval, right? It's just going to be the change in r from this point to that point divided by the change in space. Well, I could do the same thing for the second derivative. I could say the second derivative, ri, with respect to xi, is going to be equal to the change in slope. So the slope right here is going to be equal to, I don't want to really work this out the whole way because we've got a lot of other work to do. I've done this before many times, so I'm just going to write this. Ri plus 1 minus 2 ri minus ri minus 1 over delta x squared. And that's how we write a derivative in finite difference. And so really you have a delta x squared because each of these have a slope that depends on divided by delta x. And then you're taking the slope with the slope. That's where you get another delta x squared. What about the time derivative? Well, in that case, I need to also have a time component. So imagine that these are right here, and a little bit later, these are right here, right? They've moved up. So I need another index to represent time. So I'm going to have these ith elements represent my x values, right? Because each one's separated by a value of delta x. And I'm going to represent the time with another indice k. And so they're all going to be separated by a time delta t. So if I want to write the partial derivative of rik, right, that's the ith space element, the kth time element with respect to time, then it's just a first derivative. Now, in this case, I'm going to take this kth value and the next one to find the derivative. So it's just a slope. This is going to be rik plus 1 minus rik over delta t. So now I have a second derivative with respect to space. I have a first derivative with respect to time. And my two functions here have just a first derivative of time and a second derivative in space. So I can write these in terms of these equations. So let's start with this one right here. New piece of paper. So I'm going to use that function. I'm going to write this. So let's just write this out. I have h bar, now the partial of r with respect to t, and I have an I and a k element. Okay, so that's going to be equal to rik plus 1, that's a comma, minus rik over delta t. All right, I've replaced this partial derivative with a finite difference derivative. And then over here I have equals negative h bar squared over 2m. And I have a second partial of space for I. That's going to be I plus 1 k minus 2 I plus I minus 1 k. They're all the same time, right? I'm not changing time over delta x squared. And then right here I have v, so that could depend on space. I'm going to put plus vi k. Now let's solve this, right? Notice that there's only one value and one term in here that's in the future, and that's this right here, right? This is that particular element in the future because it's k plus 1. None of these others have k plus 1. So I want to solve for this term right here. Let's multiply by delta t over h bar. I get rik plus 1 minus rik equals negative h bar. No, that h bar cancels right there. One of those. Negative h bar delta t over 2m delta x squared. I'm going to factor that out. Times I plus 1 k minus 2 iik plus I minus 1 k. And then this term right here, I'm multiplying by delta t over h bar. So I get plus vi iik. I should have put the delta t over h bar. And then I just need to add this term to both sides, right? So I guess I should write it out. rik plus 1 equals rik. I'm going to move this term over to the front. No, I'm not. Minus h bar, not squared, delta t over 2m delta x squared, I plus 1k, minus 2 iik, plus I minus 1k, plus delta t over h bar, viik. That is important. Am I running out of ink? I might be. New marker. Okay, saving this. Now I need to do the same thing for this equation. So let's do that. Let's see if I can write it right here. I'm going to write it once. So I'm replacing the derivatives, right, as finite difference. I get minus h bar I get a partial, it's going to be I k plus 1 minus I k over delta t equals negative h bar squared over 2m. And then I have the finite derivative. I'm trying to write low so I don't mess up my focus. This is going to be equal to, I have I plus 1 k minus 2 rik plus ri minus 1 k, all of that over delta x squared, plus vi rik. And again, I have one thing in the future, and that's this. I want to solve this for this term. And it shouldn't be too hard. Let's see if I can just do it in one fell swoop right here. That way I'll have them together. So I'm going to multiply both sides by delta t over h bar. And I'm going to add that. So I get I k plus 1 equals, now there's a negative, right? So I get h bar delta t over 2m delta x squared. And then I get all this stuff. I should have included that other term in there too. Right up here. I'm going to put it right here. I plus. Sloppy, I know, but I should have done that before. And then I have this, ri plus 1 k minus 2 rik plus ri minus 1 k. And then I have this term. But I'm dividing by h bar, a negative h bar. So it's going to be minus vi delta t, vi ri, and again I got it backwards, delta t over h bar. That's what I want. So what we can do is, now just like with the finite difference method before for space, notice that if I start with rik, and iik, then I can find the new ones. Now there's the one problem that I'm going to have is that when I do this space derivative, I have an I plus 1 and an I minus 1. So this means that when I go through my list of values for I and R in space, the endpoints I can't change. Those are actually my boundary value anyway, right? Those are my boundary conditions. So I don't want to change those. And we did that before. Now we got to implement this in Python. This is what we want to do. So I'm going to start off, and I'm going to put this wave function to begin with, because I know that's a stationary state and should work. But still, I can plot this, calculate this, and then I also want to do this. I want to normalize it, right? So the integral from negative infinity to infinity of psi star psi dx is 0. Well, what is psi star psi? Psi star psi is going to be equal to psi star is r minus I times r plus I. And when I square that, I get r squared plus I squared. So I get a real value for the probability density, and I can integrate that and set that equal to 1. Right? So I want to do that every time I calculate my new things. This will be kind of like a check on my numerical solutions. If you don't do this, things can get a little out of hand. So we want to do that too. So we've got a lot of work to do. Let's jump over to Python and get to work. This is the equation that we need, though. Okay. No more autofocus problems. We're switching over here to Python. Python activate now. Okay, so this is the program that we had before. Let's go ahead and go to, why is that? I don't want that. Can I just close that? Okay. Here is a brand new program. I'm starting a brand new program right here. And I do want to use some values just to make things work. Let's go ahead and start off with h bar. And this, I did this before, right? We're always going to do this just because the numbers get a little, is that big enough? I think that's big enough. H bar equals 1. M equals 1. And in this case, I'm going to set the length of the well to 6. And I did, because the numbers can get a little messy, and I want to make sure that things work. So I'm just using the same numbers I had before. Looking at my other values. The other thing I need to pick are x. Well, I'll set that in a second. I need my dx and my dt. And these can be tricky. 0.1 dt is 0.0001. That's what I found works. If you don't get good numbers here, then things explode. And that's bad. Okay, let's go ahead and start off with a graph. I'm going to need a graph. G1 equals graph. X title equals X. Yeah. And then Y title is equal to, it's going to be stuff. It's going to be, I'm plotting R and I and the probability density. So I'm just going to call it stuff. That's wrong, but that's fine. Width, spell it correctly, is 500. Height is 250. That's good. Now, I want to plot the real function, the imaginary function, and the probability density. So I need 3 curves. F, R, G curve, color equals color dot, let's do this one as green. F, imaginary is going to be red. And I can put labels on these two, but I'm not going to. And then the probability density is going to be blue. And those are for graphing. Now, in terms of dealing with these finite differences, I need to put them in. I need to put all my stuff in lists. So I need to make some lists. I'm going to have a whole bunch of lists, right? I want to have a list for x. So I'm going to call, let's say xt is equal to 0. That's my temporary x. X equals an empty list. And then I'm going to need a real list, right? But I'm going to need one in the past, old. Do I need that? I don't think I need that. I can do now and new. But this is the way I did it before. I'm going to do it. So I need an old, a now, and a new. So I'm going to say R new is empty. R now is empty. R old is empty. Some people use double indices for these. I just like to, we only have 3, so I don't, that's what I'm going to do. And then for the I new, I now, I old. So it's got those three. And then I want one for the probability density. I'm going to call that PP. That's it. Okay. Let me go ahead and make, if I have A, I'm going to say K is equal to pi over A, right? And so that way I can use my normal solutions when I'm going to start with my normal solution. Oh, I need one more function right here. V equals 0, equals empty list. I need one more thing too. I'm going to need T is 0. Okay. Now I'm gonna plot my two solutions. I have C1 sine kx and then C2 plus C2 sine 2kx. So I need to pick C1 and C2. C1, this is what I used before. C1 is the square root of 3 over 10. C2 is the square root of 7 over 10. I think these values make a normalized initial thing, but we're going to change that anyway. Okay, let's start building our first list. I'm going to go down here, and this is the way I like to do it. There's more than one way to do it. I'll say while xt is less than a, and then x equals xt equals xt plus dx. So I'm going to increase my value of dx, of x, until I get to the end of the well. And I'm putting that right there at the beginning because I forget. And now I can go ahead and add all my stuff. So I can say x equals x plus xt. So that's going to add the value xt to my list x. So my list of x is going to have all those xt's in there. Now I need to do the same thing for all my r values and my I values. Now the new values, I don't really care what they are because I don't really need them. So r new equals r new plus 0. I'm just going to add 0 to that. I'm going to add 0 to I new. I new equals I new plus 0. Because I'm going to change it, right? I'm going to calculate that right away. Now I need r now. So r now is r now plus, now here's where I put my initial solution. C1 times sine k times xt plus C2 times sine times 2 times k times xt. That's my initial solution. And then my r old is going to be the same thing. Right? So I'm just going to highlight this. R old plus that. Now, what about my I now and I new? I'm just going to set them equal to 0. I now equals I now plus 0. But see, by doing this, I'm building up a list of I nows at the same length as everything else. I old equals I old plus 0. And then I need my v's too. In this case, it's an infinite square well. The potential is 0. V equals v plus 0. Okay. I think I have everything. Let's go ahead and just plot my initial solution, right? Just to make sure it's working. So I can do this for I in range, the length of xx, just x. And I'm going to go through all my values of x and all my values of r and all my I'm just going to do r. Let's just do r. Let's just do r squared. Just to test, right? Because my initial, if I did the probability density, it'd be r squared plus I squared, but I 0. And I'll do this as fp dot plot xi. Oh, I didn't add in pp. Let's see. Let's do pp equals pp plus this stuff squared. So put a parenthesis around that, squared. Let's see if that works. And then do PPI. Let's see if it works. That's a lot of stuff right there, and if it doesn't work, then it's not bad. But it worked. Haha. Okay, so that means that we should save it. and I didn't give it a name. Time-dependent Schrödinger equation 1D finite difference. I'm going to give you the code. Don't worry about that method. Save it. Whew, okay, so now we got stuff set up. I don't need to do this. I need to do this. While t is less than, let's say 5. I'm just picking a number, 5. And then the rate here has to be high because your computer's not going to keep up. We're going to go through so many different lists, so many different times. It's going to be a lot of work. But what I do need to do, if I want to make an animated graph, I need to make animated graphs, I need to set up blank lists for graphing. So that's the next thing I'm going to do. FR data equals an empty list. FI data equals an empty list. FP data equals an empty list. Now what I want to do is go through and calculate this. Those two equations. I need to enter those two equations. So whenever I see an I, I'm going to use I. Whenever I see k plus 1, that's new, right? Whenever I see k minus 1, which I don't have, I just realized I don't have k minus 1. There's no k minus 1s. So I don't have to worry about that. I made a mistake, but that's fine. I just use now, right? And then I can calculate the new. Now, to do that, I'm going to do this. For I in range 1 to length of x minus 1. Because that will go through my x values, but not include the first one because I started at 1, not 0, and not include the last one because I'm only going to x minus 1. So I don't have to worry about those endpoints. So let's update the real function first. So I'm going to type that up, just like I have my equation right there. Let's see if I get it right. R new I, right? Because that is Ri k plus 1. So it's new. Equals the now I are now, no, yes, are now I minus h bar times delta t divided by 2 times m times delta x squared. All that times I plus 1 now. So I now I plus 1 minus 2 times I now I plus I now I minus 1. And then I have that last term plus dt times vi times I now I divided by h bar. Now I need to do the same thing for I. So I new I equals I now negative. No, it's plus. I now I plus h bar times dt divided by 2 times m times dx squared times r now I plus 1 plus minus 2 times, let's see, that's good, minus 2 times r now I plus r now I minus, this is tough, minus 1. And then I have minus dt times vi times r now I divided by h bar. Whew. Okay, we got it. Hopefully. I may have made a typo. If I did it on purpose just to see if you're paying attention. Now what do we need to do? So now I want to take my old values and move them to new values. I'm going to go through the list again, which I don't have to do, but I like to do a separate list because it makes me feel better. For I in range 1 to length of x minus 1. So I'm going to say r old I equals r now I. So I'm going to move my old values to now, which I didn't really have to do because I never use r old. Let's just skip this step and see if it works, because I think that I don't need that, so I'm going to skip that step. I feel bad, but that's what I'm doing. So let's just do r now I is equal to r new I. And then the same thing, I now I equals I new I. So you can't just set those two lists equal to each other. They'll always be equal. I want to change it, right? That's what I'm going to do. Now I want to calculate the probability density function. I can do that in here. Yeah, let's just do it right here. So PPI is equal to R now I squared plus I now I squared. So now I have all my values of P. And I need that so that I can calculate, that I can normalize the whole thing. So let's say P total equals 0. And now I'm going to integrate. So I can do that for I in range. I'm going to start from 0 to the last one, right? Because if you think about integrating, I'm taking the height times delta x, but I'm going to have one less of those than I have x's. So range of length of x minus 1. If you did it just length of x, you'd get the right answer too, though. And I'm going to calculate the area right there and add it to the total. P total equals P total plus PPI times dx, right? So I'm integrate. PP has already done the psi star psi. Multiply by dx, add it up. That is an integral, and I'm done. Now what I want to do is divide my I nows and my R nows by the square root of P total. And that means that when I go back and I reintegrate, I should get a value of 1. I'm going to go through the whole thing. I can't do it in that loop. So for I in, I'm going to do it for all of them. Range, length of x, even though the first and the last are 0 anyway. R now I equals R now I divided by the square root of P total. And then need to do that for the new. Just change that E. And then I need to do that for the I's. I just paste it. So change that to I. Change that to I. Changes to I new. I new. Whew. Oh, no. Okay. That's a lot there going on. Now I need to plot the stuff. Okay. So I'm going to go through and add all my values to my plotting list. I'll do that. Can I do that here? Let's just do it again. For I in range length of x, fr data, that's what I called it, equals fr data plus my x and y values. So my x value is going to be x, which is going to be xi. And then my y value is going to be ri. And then I'm going to do the same thing for I. This is going to be ii. And this is going to be I. And this is going to be I. Oh, you know what? My probability I didn't redo my probability. I need to redo my probability. I normalized it. I need to recalculate my probability. So I think I can just do this again. Right here. And then plot that. FP data equals FP data plus XI PPI. And that should be it. All I need to do is now actually plot those. FR.data equals FR data fi dot data equals fi data. You gotta emphasize that I when you say it. fp, I did call it p, dot data equals fp data. And now I need to increase time. T equals t plus dt. If this works, man, I'll tell you what, I'm be impressed with myself. Because there's a lot of stuff. It's easy to make a mistake. I should save it. If it doesn't work, I don't know what I'm going to do. Actually, I know what I'm going to do. See, it didn't work. Can't find the variable r. Where do I have r? Probably down here at the bottom. I probably typed r. I don't see an r. Oh, ri. That's right there. This should be r new, I new. If that's my only mistake. Okay, so this, I said I was going to do a stationary state first, and I didn't. We'll change that in just a second. But this blue curve is the probability density, and it should oscillate back and forth just like we saw before. Of course, not as fast because there's a lot of stuff going on. And it does look like it is doing that. Yeah, it's doing it. It's a lot slower. We're doing a lot more calculations. This is not the best way to do this, right? But it's a way that's easier to understand, and that's what I like about it. And we could just watch this for a while. It is pretty cool. Okay, so I think it's working. Now, you get a little bit of zooming in on there because I didn't, there's auto scaling in the graph. But I think this is a great place to stop. We did a lot of work. If you made it to the end, you know I'm always proud of you for making it through this whole thing. I have trouble making it through the whole video, so if you made it through the whole video, that's really great. There's a whole bunch of other stuff we can do here. We could plot any old wave function, see how it evolves. Be careful. Some functions are not well behaved, and they kind of explode after a while. But this one's doing pretty good. I'm pretty proud of it. So I'll put a link to the code, this code down below, and my previous calculations down below, and hopefully you find that helpful. I'm pretty happy about this one. So I'll talk to you later.